Welcome to our demo for telemetry-driven continuous authentication. Our project explores whether we can correctly identify users purely based on their mouse movement biometrics. To collect this data, we use a 3D environment made on Godot. To run the testing environment, users are instructed to download the correct executable for their operating system on our repository. Today, I will be demonstrating the Mac environment, but the process is identical for Windows. Once the environment is launched, participants are prompted to complete a series of rapid point-and-click targeting trials. In a full session, the user must successfully hit 48 randomized targets. Behind the scene, the Godot engine is logging the exact X and Y screen coordinates in a millisecond on every single frame. This means a single 48 target trial generates over 1,500 rows of pure kinematic data. This high-resolution tracking allows us to capture the complete continuous trajectory, which we define as a stroke, from the moment one target is destroyed to the next successful hit. To access your generated CSV file on a Mac, simply go to the Project tab and click Open User Data Folder. If you're on Windows, you can find it quickly by pressing Windows key and R. Once you have your file, you can view your raw data by going to our provided website, or by cloning our other GitHub repository and running it locally. We built this custom visualizer so you can watch a complete recreation of your aim data and see exactly how your strokes look.
This is us showing how we go from the raw CSV files that we get when we run the Godot trial to actually training our model. So initially we start with these raw CSVs. This one's called Lewis_S3 for the third session, raw. And so it has like the timestamp, the difficulty which we don't use, player position, and target position, and it's like thousands of rows. So we run this file called segmenttrials.py, where we segment the trials into 48 rows, and we also calculate all the features so that we get a nice file that looks like this. It's 48 rows. It has many features. And yeah, so you can see here that I actually left out Pret S1. That's because the way we do this is we call this file, we give them the file path, or we give the segment trials the file path, and once we run it, you can see that Pret S1 is actually there. So we do that for every participant for every session. So 7 participants, 3 sessions, that's 21 times. And then we run combined segmented CSVs to get a nice combined file. So that's 48 times 3 times 7, because there's 48 targets. That's how many rows were there. You can see that 1008 is that number. It also lists the amount of files combined. You can see here that we have a really nice test train split, because we have a column dedicated to what session it is. So the training is only done on S1 and S2, and the testing is only done on S3. That way we're not cheating on our data sets. So after we have these combined trials, we run the train model.py, and then it outputs logistic regression analysis and random forest analysis. It shows the confusion matrix, basically just outputs all the metrics that we had in the video course, or in the presentation we did. We only covered logistic regression because it was better, so we didn't cover the random forest, which was worse. But yes, and then here is what that file looks like, although of course you can just see the file in the GitHub repository. And thank you.
Now let's look at our final results. As you can see on the slide, evaluating identity on a per-stroke basis is challenging. Since nobody moves their mouse the exact same way twice, our accuracy for just one individual click was only 52.4%. However, continuous authentication systems don't rely on a single click. When we looked at the user's entire session and used a majority vote, our accuracy jumped to a perfect 100%. Moving on to our first graph, we have the top 10 feature importances. We found that velocity and rotation were actually the biggest identifiers for each user. This makes a lot of sense since everyone's natural mouse speed is quite different. Rotation is also key because users take completely different paths after a hit or miss. Some people naturally loop and circle around, while others take a direct, straight line. Finally, looking at our confusion matrix, it is really interesting to see which users the model occasionally confuses for one another. Obviously, if we were to scale this up with a lot more users, we would need to create a more robust algorithm. In a real world setting, we would need that individual accuracy to hit 99% before letting the system run entirely in the background. Thank you for watching.